So what we're going to talk about is now we're going to talk about reduction in order. And hopefully you went and watched some of the old videos on first order linear differential equations utilizing the integrating factor, because we're going to utilize the integrating factor in order to solve these differential equations. Okay, we're going to be looking again at second order differential equations. And so kind of what we're going to do is we're going to kind of play out. It's going to be kind of a combination of variation parameters and using the integrating factor, and then also substitution utilizing the integrating factor. So kind of follow along with me. I'm going to use it in examples because kind of like the more abstract way of going about it, like how they do early on instead of the book. There's no problems with that. I just think it's a little bit difficult to follow, and I think maybe seeing some examples and following the logic of it might be better. So let's suppose that what we have is we have this differential equation. All right, so we want to solve xy double prime minus 2y prime plus 2 minus xy equals 0. And we know y equals e to the x is a solution to this dE, or actually the homogeneous differential equation. So that's one of the things that we're going to need is we're going to need a solution to the homogeneous part of the differential equation in order to use the reduction in order. It turns out that this differential equation is homogeneous, right? A couple things to notice. Notice here that we have, that we don't have necessarily constant coefficients. So we can use reduction in order even if we don't have constant coefficients. It's totally fine, okay? What we're going to do is we're going to say, okay, let's posit that we've got our first one, y1, is e to the x. Let's say that we have y2, and we're going to say, well, y2, we're going to say is going to be u e to the x. So for u of x, some function of x. So very similar to the variation parameters, what we're going to do is we're going to say, okay, well, let's suppose that we have a function that we're going to multiply by our solution to see if we can find another solution, okay? Linearly independent solution. All right, so what I'm going to do then is I'm going to say, okay, well, then y2 prime is going to equal u prime e to the x plus u e to the x. And y2 double prime then is going to equal u double prime e to the x plus u prime e to the x plus u prime e to the x plus u e to the x, which is just equal to u double prime plus 2u prime e to the x plus u e to the x. Then we're going to resubstitute that back into our differential equation. Okay, so this is going to now be x times u double prime plus 2u prime e to the x plus u e to the x minus 2 times u prime e to the x plus u e to the x plus 2 minus x u e to the x equals 0. So what we're going to do now is we're going to kind of situate this so that we can simplify it, and we're going to turn it into, what's going to end up happening is we're going to turn it into a first order linear differential equation. So that's kind of what we want. Although along the way, what we're going to have is we're going to have a function that's only in terms of u double prime and u prime. So what I'm going to do first is I'm going to actually group together all the u's, right? So this is u times x e to the x minus 2 e to the x, right? Here's that second term, okay? Plus, and then we'll have 2 minus x e to the x, okay? Minus, now we're just going to use the rest of the parts. This is going to be plus 2 u prime x e to the x plus u double prime x minus 2 u prime e to the x plus, and then we don't have anything else. And that'll all equal 0. Okay? So now, this piece right here, okay, if you remember, e to the x solves x y double prime minus 2y prime plus 2 minus x y equals 0. Okay? So this whole thing, that whole thing that I just showed you, so the u's cancel. And that's actually what's going to happen every time here. Okay, so all the u terms are going to cancel. And what we're going to be left with is the rest, this portion right here. Okay, so that's going to be u double prime x plus, and then I'm going to take u prime, and that'll be 2x e to the x minus e to the x. So what I'm going to do now is I'm actually going to discuss reduction in order. This is 8.9. And reduction in order is a way of solving differential equations or higher order differential equations if we have at least one solution. And it's going to become very similar to utilizing the integrating factor for first order linear differential equations. So you want to make sure that you've gone through and reviewed that in case you've forgotten that. And also it's going to have some parallels to reduction in order and also some substitution that we did when we did first order differential equations. Okay, so it's kind of like what we're going to work with. I think that utilizing some examples is probably the best way of going to show this method. Like a generalized way of doing the method can be a little bit confusing. But if you're interested in doing that, it is inside of your book, and you can take a look at that. Okay, so let's say, for example, we want to solve. Okay. Xy double prime minus 2y prime plus 2 minus xy equals 0. Okay, and similar to the variation parameters, what we're going to need is we're going to need one of the solutions. Okay, we will need, or actually not, in this case, we only need one of the solutions, unlike variation parameters where we needed two. Okay, we will need y equals e to the x solves Ly equals 0, solves the homogeneous part. So in both cases, we're going to need that to solve the homogeneous part because it's going to allow us to kind of like do some cancellation, very similar to what we did in variation of parameters. Okay, so what we're going to say is suppose u of x or y equal to, we'll call it y2, u of x e to the x is a solution to the above. Okay. So e to the x is our y, okay, and we're going to multiply that by some function u of x, and we're going to posit that's the solution, right? So we're going to solve for u, okay? So similar to every other one that we did, what we're going to do is we're going to, take a couple derivatives, plug them in, and then try and find u utilizing some system of equations or some tricks. That's differential equations. Just do some tricks, right? Clever stuff. So we have y2 prime is going to equal u prime e to the x plus u e to the x. Okay, so there it is, right? Because it was u e to the x is y, so that's the derivative. And then y2 prime is going to equal u double prime e to the x plus u prime e to the x plus, and then u prime e to the x plus u e to the x. Okay, which equals u double prime e to the x plus 2 u prime e to the x plus u e to the x. And now we're just going to plug it back into our differential equation. So we're going to say, okay, x times u double prime e to the x plus u prime e to the x plus u prime, plus 2u prime e to the x plus u e to the x minus 2 times u prime e to the x plus u e to the x plus 2 minus x u e to the x equals 0. Now, what we're going to want to do is we're going to want to get rid of some of these pieces. In particular, what we're going to really want to get is we're going to want to get all of our terms in terms of u double prime and u prime. So somehow we're going to have to get rid of all the u's, all right? But it turns out having one of those solutions is going to make this, it's going to allow us to do this, okay? So let's first group all of our u's together. So this gives me now u times x e to the x, okay, minus 2, right? So there's that term, okay? And then here's this one, minus 2 e to the x plus 2 minus x, right? Because here's the last term, e to the x, okay? Then we'll have plus 2u prime x e to the x, or excuse me, let's do the double prime. We're going to have u double prime x e to the x, okay? Plus 2u prime x e to the x minus 2u prime e to the x equals 0. Now this whole piece right here, it equals 0, okay? As e to the x is the solution to the dE, okay? Right? So what we know is that if I plug in e to the x into this one up here, right, I actually solve it. So consequently, this whole term here is equal to 0, because this is, right, this is y double prime, y1 double prime, here's y1 prime, and here's y1, right? Okay? And that's going to happen every time that we do utilize reduction in order, right? That's going to reduce the order. That's what it does. So we're going to be on the lookout for that. If you're not doing that, you're doing something wrong. So what we're left with now is we're left with u double prime x e to the x plus u prime 2x e to the x minus 2 to e to the x. And that equals 0. So what I'm going to do is I'm going to divide by x e to the x on both sides. Okay, so divide by x e to the x. So 1 over x e to the x, 1 over x e to the x. Well, the right-hand side is 0. That's easy. The left-hand side is going to give me u double prime plus u prime times 2 minus 2 over x, and that equals 0. Okay? Now what I want to notice is I want to notice that if I substitute w equal to u prime, then w prime equals u double prime. And what that gives me then is it gives me w prime plus w times 2 minus 2 over x equals 0. This is a first order differential equation. It's a first order linear differential equation. And since it's a first order linear dE, I can use the integrating factor in order to solve it. Okay? That's basically one of the ideas. One of the big ideas, actually, if you ever get into ordinary differential equations, is, oh, wow, I now have something that reduces to a first order that I do know how to solve. Okay? So, I of x, okay, is going to equal e to the integral of 2 minus 2 over x dx. All right, remember that? And so this is going to end up equaling e to the 2x, and then I'm actually going to make it plus, okay, actually, let's do it this way, equals e to the 2x, right, plus, and this will be ln x to the negative 2. And so this is then going to equal x to the negative 2 e to the 2x. All right. If you remember, we multiply both sides by the integrating factor. Okay. So then d dx, we're going to end up d dx of w x to the negative 2 e to the 2x. Okay. And that's going to then just equal 0. All right. Then what do we do? Integrate both sides. The integration of the left side is going to leave us w x to the negative 2 e to the 2x, and the right side is just going to be a constant. We're going to call it c1. So w is going to end up equaling c1, okay, x squared over e to the 2x. So now that we have that, right, okay, we want to recall that w equals u prime. And we're actually looking for u. So we need to take the integral. We take the integral of u prime is going to equal the integral of c1 x squared over e to the 2x, which is going to equal, which equals negative 1/2 e to the negative 2x minus 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. Okay. And all of this multiplied by c1, okay, plus a c2, right? Okay. We're actually going to change those to c2 and c3 because this is now all going to be multiplied by e to the x. Remember? Okay. Well, I'm not going to do that right now, but I'll do it in just a second. We're going to multiply all of that by e to the x because, right? Okay, e to the x was our first solution. So y, our full solution, is going to be c1 e to the x, okay, plus, and this will be c2, okay, c2, right, times negative 1/2 e to the negative 2x minus 1/2 x e to the negative 2x minus 1/4 e to the negative 2x, okay, all multiplied by e to the x. Okay, you can go in and simplify that because it's algebra. You can do this. Okay, all right. So that's actually how we go about finding it, right? What we're going to do, it's very much a process. I'm going to do another example in just a second. And that process, what it entails is okay, first, right, I'm going to posit a solution, okay, u times u times the solution that I already have, okay. Then I'm basically going to plug that in so that I can solve for u, right? But the trick to solving for u, okay, is to eliminate all the u terms, right, so that you're left with only u double prime and u prime, okay? Then make a substitution. Once you have the substitution, you now first order linear differential equation. You can use the integrating factor, okay, to solve for what we substitute for, call it w, all right? And then we integrate to get back to u, okay? So let's try that again. So let's solve the dE, x squared y double prime plus 3xy prime plus y equals 4 ln of x, okay? And suppose that we know that y1 is equal to x to the negative 1, all right? So what we're going to do is we're going to posit y2 is going to equal u x to the negative 1, where u is a function of x. So y2 prime is going to equal u prime, okay, x to the negative 1, and then minus u x to the negative 2. And then y2 prime is going to equal u double prime x to the negative 1 minus u prime x to the negative 2 minus u prime x to the negative 2 plus 2u x to the negative 2. Or u x to the negative 3, excuse me. Okay? All right. Then we're going to plug it back into our differential equation. So this is going to be x squared times u double prime x to the negative 1. And this is going to be minus 2u prime x to the negative 2. Okay, plus 2u x to the negative 3. Okay. All right. Plus 3x times u prime x to the negative 1 minus u x to the negative 2. Okay. Plus u x to the negative 1 will all equal 4 ln of x. Just like in the last time, right? Group your u's. All of our u terms are going to go away. We'll show that in just a second. So this is going to end up giving me u times x squared x to the negative 3. And I want you to notice I'm not actually going to simplify. We'll do that in a moment. I want to demonstrate something. So it's going to be x squared x to the negative 3, okay, plus 3x, or rather minus, yes, 3 plus minus, or plus 3x, okay, negative x to the negative 2, okay, and then plus u x to the negative 1, minus, and then x squared times x to the negative 2, we're going to get minus 2u prime, and then x squared times 2u x to the negative 3, that's going to give me Oh wait, we already did that one. Actually, we need the u double prime. So this is going to be plus u double prime x, and then the 3x u prime x to the negative 1 is going to give me plus 3 u prime equals 4 ln of x. Now, this is x to the negative 1. Actually, excuse me. Yeah. That should be x to the negative 1. That's actually, that's y1. This is y1 prime. Okay. And this is, excuse me, this is y1. This should be a 2. This is y1 double prime. Okay, so it's this term right here. It goes right there. Okay. So that's going to be y1 double prime. We have y1 prime and y1. So that means that this whole term, right, all equals 0, as y1 is a solution to the homogeneous differential equation. It's going to end up equaling 0. So what we're left with is u double prime x plus u prime equals 4 ln of x. Okay. Then what I'm going to do is I'm going to divide through by x, right? So I'm going to divide by 1 over x on both sides, and that's then going to give me u double prime plus 1 over x u prime equals 4 over x ln of x. And so now what we need to do is we just need to solve this differential equation, okay, using an integrating factor. So now we have this, u double prime plus 1 over x u prime equals 4 over x ln of x. So now what we're going to do is we're going to do a substitution. We're going to let w prime, or w, equal u prime, and w prime equal u double prime. So that means that we now have w plus 1 over x, 1 over x, w prime plus 1 over x w equals 4 over x ln of x. Okay, and now we find our integrating factor. I have p of x. P of x is equal to 1 over x. The integral of p of x is thus dx is going to equal then ln of x. Okay, so e, our integrating factor, I of x, is going to equal e to the ln of x, which simply equals x. Okay, multiplying both sides by x, what we end up with, right, is on this side we get d dx times w, okay, x equals, or wx prime rather, equals 4 ln of x. Now I just need to take the integral of both sides. So I get both sides. And what we left with is wx equals, okay, 4 times ln, or x ln of x, minus x plus c. Call it c1. All right. So then w is going to equal 4 times ln of x minus 1 plus c1 over x. We'll resubstitute. And we'll have the integral of u prime, okay, which is what w is, right, is equal to the integral of 4 ln x minus 1 plus c1 over x. Okay? And just to finish this up, that means then that u is going to equal 4x l times 4. That's 4x ln x minus 4. That changes to 4. That's going to be 4x ln of x minus 4x minus 4x plus c1 ln of x plus c2. Now, if you remember, y1 equals 1 over x. So what that's now going to give me then, okay, is that u my new y is going to equal 4 ln of x minus 8 plus c1 over x ln of x plus c2 over x. And this is y2. So my complete y is going to equal, right, c1 over x, or actually we have it right here, it's our c2 over x. Okay. So that's actually going to end up being our full y. Y is going to end up equaling 4 ln of x minus 8 plus c1 over x ln of x plus c2 x. Okay. So something to notice here that when you complete reduction of order, okay, we have the entirety of the equation. We don't actually have to add on the piece, it's already there, right? We don't have to add on the homogeneous piece. The homogeneous piece is already there. And that's in fact what y is. Okay? So this is how you do reduction in order. All right? Very tricky, very clever. Okay, whoever was doing this, very smart. All right. So this concludes the lesson.